So welcome to the pre-recording of lecture 38. So this is the second half of our session 19 in the 8-week summer course. We are in the middle of the 7th week, actually just past the middle of the 7th week. We are going towards the end. In the first half of the session, in the previous lecture, threads were introduced. With threads, we can build concurrent models. A concurrent model or a concurrent program executes multiple tasks independently from each other. So you don't get true parallelism because of the interpreter lock, but you have concurrency. So what's the point? Well, in this lecture here, we're going to explain how to do a predator-prey simulation. The prey are the frogs. So frogs are hopping around in a pond. There will be a graphical user interface to kind of give somehow the feeling, give some kind of an impression what we are modeling. The predator or the predators are flying birds. Birds fly over the pond, see the frogs, get hungry, they eat them. So we introduced the distinction between the heap and the stack last time. Anything that is dynamically allocated lands on the heap. Lists are passed by references, and we are giving the birds access through to the pond of frogs, to the swamp, via a reference to a list. So the concepts that we have introduced during this course and in the previous lectures are actually very useful now in this application. So it's also a self-contained introduction to object-oriented programming. So what is our model of a frog? So what does a frog do? A frog hops around. In a way, this is another extension of a random walk. In one of the graphical user interfaces, we had a moving dot. So now we have, instead of a dot, we are imagining that we have a frog that hops around. So the life description of a frog is very much restricted here. This is certainly not a realistic model in any way, but for our purposes, a frog actually has a position. It has a certain lifespan, so in its life it can do a number of hops. There are the characteristics of the every hop it does, how far it hops, and in between hops there is a delay. So every frog is characterized by these data attributes, and these data attributes, the step size, the rest time, the hop limit, and there is the randomness. Even if you make it the same for all the frogs, then the randomness will still give some individuality to each and every frog. It's therefore also kind of unnatural that you would tell a frog when to hop at each time. You could still do this via a top-down way, but it's very unnatural way of thinking. So threads are important. We have seen the unified modeling language, which lists all the data attributes and the functional attributes, so the hopping and the running. So this is in preparation of the thread class. So Python provides a thread class in a threading module. So we will make a class to represent a hopping frog. So concurrency here helps a lot. So we will also illustrate multiple inheritance. So our first model of a frog will come in handy to recycle all the data attributes of a frog. So our first class is very basic, just to get us started again with what classes are. We can gradually build up our programs by inheritance, extending existing classes with additional data attributes, additional methods. All right, there will be a GUI, so animations are important. And at some point at the very beginning of the sequence on graphical user interfaces, I demonstrated a sliding puzzle and then indicated very briefly how one can bind the events of the mouse to the canvas. Here I will see another illustration, perhaps go a little bit slower here. In the animation, the user can place the frogs in a pond. And then there are three buttons that define the animation. The animation can be started, can be stopped, and can be cleared. So in the clearing, we actually are wiping out all our frogs, and actually we are killing them. So how do you terminate a thread? Um, so that's an interesting problem. I'm using this graphical user interface to demonstrate the termination of threads. Um, we've seen the ASCII arithmetic, so I could have used numbers for the names of the frogs, but we can compute with these letters. And there won't be any more than all the letters in the alphabet. So the names of the frogs are letters. And what we will see moving is actually the moving letters. So there will be an alphabet soup moving around. Here is a screenshot. A pond with 6 frogs, so 6 letters. It's a square canvas, so there is a label on top that indicates where the last frog was placed. And then at the bottom we have the 3 buttons for the animation. I will demonstrate this in the second part of this lecture. Okay, so flying birds. So the birds are the predators. So we will also directly inherit from the thread class now to represent a bird. So a bird can fly and eat. So the bird also has a lifespan. So it will do a number of runs over the pond. In order to direct the flying, it needs a direction in addition of a position. So in an earlier GUI, we modeled lines as base point and then an angle for a direction. I could have also done it here, but I picked a tuple of 2 integers for the flying direction. So every bird has the lifespan. So this is defined here, the fly range. There is also a delay. Every time a bird lands, it waits a little bit before continuing to the next trip. And it will eat frogs that are close enough. So there is an algorithmic element here. So in object-oriented programming, objects, classes, and the relationships between the classes are most important. In a procedure-oriented language, algorithms are important, but the algorithms are always important. So in an object-oriented program, they are encapsulated in methods of classes. And they could eventually belong to modules as well, that are then imported at the spots in the classes where they are needed. Okay, here is the class diagram for a bird. So we have the 3 functional attributes, fly, eat, run, and then the 5 important data attributes. Again, this is a very limited view of a bird, but it will be the view that we that will be sufficient for our simulation. So I will, by the way, also show how to draw these diagrams without go to the diagrams that are provided with the Jupyter notebook. In some sense, this is an alternative way to draw these diagrams. All right, the nearest frog is something that so that's an algorithm that every predator has to execute. So there is an algorithm that runs here. So we need to compute of all the frogs, we have their positions, but we need to compute the frogs that is closest to us. So this is solved by this algorithm, finding the nearest frog. But it's also solved by an abstraction. So we have to make sure that somewhere we have to have all the frogs sitting together. So typically in a list, so the list is here encapsulated. So the frogs, what you see here, is the data attribute in the frog pond. And the nearest frog will operate there. So this is a class that is sitting in between the abstraction of the frogs and the abstractions of the birds, in between the representations of the prey and the predators. All right, so then the last script that makes this all run gives a very basic simulation of a swamp with 4 frogs. You can see the coordinates, they are kind of artificial. So they are situated in on a square, on the corners of a square, uh, well separated out. They each have the same lifespan. They will each hop 20 times, wait 2 seconds between every hop, and the distance that they hop will be 5. So they are located in this swamp, which is an instance of the frog pond. So the frog pond is just instantiated with a Python list of these 4 objects, these 4 frogs, which are representing the prey in our simulation. So every class, thread frog, frog pond, belongs to a module. Every module also has a self-contained test program. I may show this in the second part, but in the second part I will scroll through a Jupyter notebook and going through each and every class that is being used. All right, as a test of the simulation, so in some sense this is a very simple start of a simulation. We have the 4 frogs, so 10, 10, minus 10, 10. Here we have 10 minus 10, so if you think of the Cartesian coordinate with the origin at the center. So there are the 2 arrows that are drawn here. So there are 2 predators, 2 birds that are flying into this pond. They land somewhere and then they look among these 4 frogs which is closest. In the meantime, the frogs are hopping around. And you could see, so you will see that this can add some indeterministic aspect in this simulation. All right, before I go to the second part, so let me summarize the classes. So the program, so there's one last program. This is the birds, the flying of the birds. That will be, so the central part there is the representation of every bird. Starting out at the left is the thread frog class. The thread frog class will actually inherit from the first frog class that we will make. And in between is the algorithm to compute the nearest frog. So the eat, so you could see this still as a main program, but it's kind of difficult now to decide. You could see the main program from the perspective of the predators and see them run, but they have a lifespan on their own. There is the simulation also that comes from the lifespan of the thread frogs. So deciding here from which perspective should you write the main program is already very difficult. So you see that threading actually resolves that decision for us. We don't really have to look for do the birds live longer or do the threads live longer or do the frogs live longer. Doesn't really matter. So the algorithm of computing the nearest frog is encapsulated in the frog pond, where we actually look at the list of frogs. And given a location, we look for that frog that is closest to that location. So when we think about that problem, we don't really think about the flying. So it's just, or what is the particular eat radius? It's a parameter there. It's not even a parameter here. It suffices that we know the distance to the nearest frog. Then that is compared against the eat radius. So you can see that you can clearly separate also in the important parameters in the simulation are essentially defined in the data attributes, properly organized in the two classes of actors here, the prey and the predators, the frogs and the birds. All right, this goes towards a more elaborate GUI at the very end. So the last exercise asks for extension. So there is a fourth project if you still have time to spare, or the summer will not be over after our 8 week. If you want to do more programming towards the next course, you can work on this graphical user interfaces. Uh, what is important here for the exam questions more is that you can get around with the modeling. So if you had to work on any, if you had to work on the GUI, for example, how would you model the GUI? What would be the characteristics? What would be the widgets that you would be using? Um, so that you should be able to describe that and also use um, modeling the modeling diagrams. Okay, so we've seen the game of life. So there is also the nearest frog. So if you run the GUI for the simulation of the frogs hopping around in the pond, you can see it in this letter dance. You can see that they sometimes join. They come very close to each other. And you could extend them. This is a simulation of another way of a game of life. Whenever frogs come within a certain radius of each other, there is a new frog that will pop up as a result of their encounter. So you could, that would be an alternative to the game of life. The birds, they fly in a fixed direction. So you could have that the birds kind of locate the frogs and they fly towards them. You could also equip the frogs with kind of that they are aware when they are resting, they are aware where the birds have landed, and that they won't hop towards a bird. Uh, Here the scripts contain a main program. So the main program could actually be better in a GUI. So in transitioning, in building the GUI, you could start from the main program that is in the script for the flying birds, where also the class bird is. Okay, so the first 20 minutes are over and I have outlined, I hope, the design of the application that we are going to consider. So in a way, this is more the purpose of the lecture is more to apply what we have covered so far. The first section in this Jupyter notebook is in a way a self-contained um, introduction to the um, object-oriented design. Here you see the class diagram of the frog. So I had it in raw. So if it's properly formatted, then you see you have the class diagram with the name of the class and the names of every data attribute and the name of the functional attributes. In this description here, there is a phrase next to every attribute. So in some sense, it's a more basic way of working. So if I make the raw format of the cell, then you can see the three backticks, the three right quotes. I'm sorry, the left quotes, the three left quotes. Three consecutive left quotes allow you to introduce something that will be formatted as you see it. In a way, we have also covered markdown tables, and I'm now thinking that a class diagram could actually also be represented by a markdown table. But this has the benefit that it's very, very, very basic, and it is very useful in preparation of the class. So here is a model of a frog in a class with three simple methods. So there is the constructor. So for every frog, we will store its name. Every frog has an initial position, an h, which is the size that it hops, the delay, the resting time between the hops, and then there is the lifespan. It does m hops, so every frog can do a number of hops, and that is kind of predetermined. But there is some randomness there. So in some sense, the fact that you could say that this m is kind of an average lifespan, depending on then. So here you see in the hop method, every frog will generate a random number in between 0 and the resting time, and then it will sleep for that amount of time. So this actually adds to the lifespan. It will determine a next direction. So here it will generate a random number. -1 goes to the left, 0 stays, +1 goes to the right. This is multiplied by the step size. The same with the direction going up, down, or staying. So this hop is kind of what is executed in the run method. So you could still see this as if using a word that is used in software engineering, a refactoring code. You could essentially start with a top-down program where you have this simple loop, and then in this loop you write down based on the parameters that is defined on top. What is defined on top? All the important parameters in your simulation you put in the constructor. So these are the data attributes. This has then the benefit that for the hop, you don't really need to provide any parameters. So you could see this also as from going from a function to a method is kind of eliminating all the parameters that you would need to provide. So the hop limit is decreased. So I mentioned the problem of killing off a thread. That is a very useful thing here. So as long as the hop limit is still positive, the hop will still happen. All right, so that was the introduction. Oops, let me run this. So for one frog, Kermit is the kind of obvious name, Kermit the Frog. And you see Kermit the Frog was made with a lifespan of 4 steps. Started at minus as +10 and ended up at 5 taking hops of 5 and waiting at most 2 seconds between the hops. All right, fine now. Where comes threading in? Well, here you see threading. So this is another illustration of threading. Try to be as self-contained as possible. We import from the threading module the thread class. Our thread frog now, will inherit from the thread class, and it will inherit from the frog class. So we need to inherit from the thread class, but why inherit from the frog? Well, we have already dealt with the lifespan of a frog, how we want to model a frog, and that's fixed now. We don't want to think about this anymore. So all these important parameters are actually defined or copied in when we call the constructor of the base class here. So whenever we inherit, we make objects, we instantiate the objects of the base classes. So then there is a run. So here this run is now very important because in the previous class run was kind of arbitrary. But the run here, that's the built-in method that must be redefined with the instructions that you want the thread to execute. So every thread that is made, every instance of this class, when you start the thread, it will actually run through the instructions defined in this method. So there is the self hop. The self hop is the hop of the frog class. So that's another thing that we inherit. So we inherit the hopping from the frog class. We can't inherit the run because the run is something else. But here we have the run explicitly defined. All right, let's do the simulation. So we make two frogs, one at +10, +10, one at -10, -10. Will they ever meet? So one frog has a longer lifespan than the other. And they also have vastly different hop sizes. You see Bob hops a lot wider, so Bob actually hops till 20 -25. The first frog actually returns to its current position. Okay, so they actually, you can see the locations, they actually never met. Okay, so in threads, so there are three stages. So there is the born, there is the running, and then there is the dead stage. So these are the three major stages. There are many other intermediate stages of the threads. Threads can be waiting, they can be blocked, they can be sleeping, but they all are born at some point. They are made ready for running, so that's what the start does. And then when after they're running, so after the join here, this is a blocking instruction. So you can see creating the frog, starting the hopping, and then as soon as the hopping has started, the waiting happens. Perhaps I should run this again to make the point. You see waiting for frogs to finish. So the execution cell is actually blocked before the first join. And you see these two frogs, they started out in 2 points, but the parameters are such that they didn't meet. So actually Bob was hopping away farther away. All right, as an intermediate before we get to the predators, so let's look at the graphical user interface. So we will have a canvas at the center point of our animation. I will introduce how the mouse bindings are done. So we have a canvas, buttons in the animation, and we have labels. Here you see what happens with the button pressed and button released. So these buttons pressed and buttons released are connected to the canvas with this bind method. So there is the button pressed and there is button release. And this is very, I mean, it's not too cumbersome, and it's platform independent. And also whether you do this on a laptop with a trackpad or whether you do this with an actual mouse, it shouldn't really matter. So that's the whole benefit of prototyping graphical user interfaces with the Tkinter in a Python. All right, so there is the animation. So animations do have an important state, whether the animation is running or not. So this is the go hop. There is the size of the canvas. There is the message box that gives instructions. So initially, the message box uh, is um, set to putting mouse inside. So the message box is also the provided with a label. So actually the message is actually the label. So this is a text variable that actually will change because it's a variable, it's a string variable. So we've seen int var, double vars, now actually we see a string var. So this is a variable string, and you can embed it in a label. So actually the label will actually also change. So a label we introduced as a very static. You could just put text in there, but here the label essentially will also change. Then we have our square canvas. We always pass through the constructor the window, WDW. The binding of the buttons, and then we have these start, stop, and clear. So these will be the three methods in the animation. The grid is being used. So if you write your own GUI, at this point in time you actually run it. So I'm still giving here a very um, counter to how programming actually happens. Execute early and often. So don't start to uh, type in because this class is already kind of elaborate. So there is then the new frogs. So how the new frogs are being made. So there is a counter. So the frogs is the list of frogs. So these are all the objects. Um, how do the frogs actually come in? So the frogs, so in this Jupyter notebook, there is already the frog class that is working. So when we make a new frog, so here it is, I wasn't looking properly. A new frog is being made here in this new frog. So I have already executed the uh, code cell that contains the definition of the thread frog. In the script, the class thread frog will be imported in the script. And from that class, we will import the definition of the class thread frog. So we can treat frogs, there are threads, but we can treat them just as objects. So what we do when we make a new frog, well, we append it to the list. So that is in the stage where the animation is being defined by the user. So the user clicks on things, clicks on points in the canvas. There is the drawing of the frogs. So here you see the text essentially. So every frog is represented by a text. It is tagged by the same text. So when we draw the frogs, we query their position. So that's a tuple. We get their name. We delete the label with their current position, and then we are going to place. So here you may wonder why not just drawing this. Well, we adjust the position using the donut topology. When a frog hops towards the left, we may see it appearing back to the right of the pond. So it's a pond that's actually spherical. So the pond stretches out. The start and the stop button. So the start button, so we have the list of frogs already in a list. And with the start button, we can decide when the animation starts, when the threads start running. So early on in the previous lecture, in the first half of the session, I had a producer and a consumer thread. Here actually I have a whole list of frogs. And for every frog in that list, I start the hopping. And as long as this self.goHop is true, we will draw the frogs, refresh the canvas after 10 seconds, and update the canvas. All right, then the killing of the frogs. How does this actually happen? Well, you can't really, as a Python programmer, stop a thread once it is running. So that's why you kind of, if you want to stop really a thread, you need to either provide a condition that it will actually terminate. So when you kill a frog, what you do is you set the hop limit to 0. So for every frog that is in the list, you set the limit to 0. And then we start popping the frogs one after the other. This is resetting all the frogs. You can also restart them. So you can make new frogs, give them actually another life by, if you pop the frogs, you can store their position and you can make new frogs out of it and append them. So this is a list of new frogs. This is resetting all the frogs. So essentially restarting the animation. All right. Um, Here is the clear. So the clear actually will, so this is the stop, what happens when you stop the animation. So that's, but you still want to, so this is the clear then, where you kill everything and you also clear the canvas. The animation of the animation is actually then simply stopped. Um, I should probably demonstrate this now. So there is the buttons, the button pressed, button released. So there is the message that is there. And then actually when you release the button, um, you will make a new frog and you will draw the frogs. So that will actually update the canvas. All right. Let's run this. So what you see now popping up is the square canvas. So put the mouse inside the box to place the frog. So this is the string var. So you see, if I do this, I can place the frog there. So you can get some feeling of the canvas coordinates again. So I have placed 6 frogs. Let me start the animation. You still see, or perhaps you don't see this, well, you see it. You see it in scrolling by here. You see that all the messages that are being printed. So this is from the hop of the thread class. So this is still inherited. So let me stop the thread. So you can probably wait for some of the frogs to leave canvas, and then you see there is an encounter between 2B and D. They kind of seem to hop towards each other. I'm stopping the animation now. What happens if I start? Well, the stop is actually a pause. So I stopped the animation and actually I made a new list of frogs. So with the same thread attributes again. So I was saving the position when I was popping them. So stopping them pauses the simulation. I don't know if I have any messages that are being printed. So yes, so resetting all frogs is here. And then I restarted the animation. I can clear, and clearing actually allows me to restart everything. Okay. So there is a dynamic aspect. So whenever I click on this, so let me put some, yes, so here you saw the frog B was at the bottom, and then it appeared again at the top. You saw the donut topology. All right, enough play. Let's go to the last 10 minutes to the um, oops, so I killed off the window. So in some sense, you see the threads are still running. I've kind of lost control over the threads and they are still running. Oopsies. So let me see if I can. So yes, so the main loop is still stopped. So the application, as far as I'm concerned, is still stopped, but the frogs are still happily hopping around. So here I probably have to restart the kernel and clear all the outputs. And this should clear everything. All right, I may now, in order to continue, I need to run the definitions of the classes. I will do so. Um, and perhaps I could also have shown the actual scripts. Okay. The pond of the frogs now. So this is where the nearest frog method comes in. So here you see already the nearest frog. In the class frog pond, for the distance I need the square root. So the frog pond will store a list as its data attribute. So it will also be made by a list of frogs. Very basic. There is the static method here. So a static method is a method, it belongs to the class, but actually it doesn't have any proper data attributes. It doesn't have a self to it. So in the distance, I just want to take a square root of the sum of the squares of the x and the y coordinates. I wanted to have that separate there as a helper function. If I didn't know about this decorator static method, then I could have encapsulated this in a helper module and imported that helper module. Or here in the Jupyter environment, I could have had a code cell with this function simply defined. But it's kind of cleaner to have it as encapsulation of this distance. You see how I call this? So there is I can't really call this with self dot, but it is a class-wide functional data attribute, if you like. You have to give the name of the class and then the name of the function. That is a static method. So I run over, if there are no frogs living, then I return -1. I don't return any frog, and then there is also the third element, that is the position of the list. So I will return the distance, the frog, because that will be eaten and killed, and I will also return the position of the frog. So here the algorithm of finding the minimum distance in a list. So it's good that we kind of know the algorithms, the basic algorithms, even if Python does have a minimum. Um, you could put this in a list comprehension. So for every frog, you could compute the distances and then take the minimum of that. But I also want to position and I want the name of the frog. So just having the distance as the minimum wouldn't really suffice. I would actually still then need to look up the index and also get the frog there. It's possible to do everything with list comprehensions. Okay, let's test this. So I have a swamp, a pond frog. I have Anne and Bob. And if I take the position 5, 5, then I should actually find that The nearest frog is the first frog, the frog at position 10, 10. So this is a very simple, basic interactive test. So I'm now giving the presentation of this application also from the top down properly, like I have foreseen this shortest distance. But in actual practice, you actually start with the class flying birds and with the main application, and you kind of see that you need an upper abstraction. That's how it actually did go about. Um, so let me go now for the last 4 minutes for the actual simulation. So here is the class diagram of a bird. We inherit immediately from thread. We have the class bird defined here, and the swamp, oops, is already defined. So the swamp, so it's good that actually I checked this out. So swamp will be defined here. But Python is dynamic, so there were no syntax errors when I executed the code cell. It did not execute it. But the swamp is actually only defined here. So swamp is actually playing the place a little bit as also the object that represent the frogs. Frogs is just a list. So you see what happens when a frog gets eaten. I find the nearest frog, the prey. There is a prey, so I get the name. I find the nearest frog. If it is within the eat radius, um, if it's not within the eat radius, it will still be printed. Otherwise, it will be gobbled up, and it will be deleted from the frogs. I don't think I killed it properly because you will see that sometimes it will still. I should actually set. Oh no, I do set the hop limit to 0. Um, so in some sense, it's good that all the data attributes of the frogs are public. So when the birds are eating the frogs, they are setting the hop limit to 0 and effectively thus killing. Also, the frog actually, so the prey, the last index, prey 2, is actually the index. So this is where the delete on lists is practiced. So we want to make sure that the same frog is not eaten multiple times. So that is the important eat function. The run is in some sense still the lifespan of the birds, um, same as the run of the frog essentially. Then the data attribute, and then the flying. So the flying kind of replaces the hopping. Um, Not much new. You see, we work with templates. If we know how to model a living a frog, we also will model a living bird. So this presentation could have gone in the opposite direction. So I have one more program to show. So this is the simulation. So I have the swamp. So then we have two predators. So they fly in the direction 1, 1, and the other one flies in the direction -1, -1. And then you can see what is happening. So we have the swamp with the 4 frogs that are happily hopping around. The birds are computing the nearest frogs, but the eat radius is 5. So nothing happens to the frogs here. So the nearest distance, bad. Um, so then another round. So the frogs are hopping around. Um, and then you see the dramatic events here. 2 of the frogs are hobbled up because they are at a distance. So Dave is hobbled up here, Bob is hobbled up. Um, and let's see if any of the frogs are surviving. So we still have Anne and Cindy that are surviving in this simulation, but Cindy also is gobbled up when it gets too close. But it looks as if I missed this. It looks as if all our frogs are Oh, Anne actually simply expired. I think that might be the case. So we don't hear of Anne anymore, but Anne might simply have expired. Or within the simulation stops when the birds have finished their flying ranges. And yes, so Anne is still here. Anne is still alive. All right, so I'm at the end now, very at the very end. So there is one final script. So this is the final script here. So the simulation is defined in this main. So typically you would run this in a terminal window. Um, and you see the imports. So the classes are defined in the module. So we need the frog pond, we need the thread frog. Um, and that is it. So in this lecture, we have not covered really something really new that we have not covered before, but I think it's important to see more things in context. So this is a larger application where we could see the benefit of concurrency to modeling proper live topics. Okay, I will stop this pre-recording now.